Hello. Today I'd like to address one of the main issues I have with working with analog signals with the Arduino, and that is the fact that you can take an analog signal from the outside that has a value between 0 and 1023, so 10 bits. But if you want to output that signal again from the Arduino, you will have to use a PWM pin, which is 8-bit in size, so you get the value between 0 and 254 out. So that's a division of 4 just by taking the signal through the Arduino. And that's what I'd like to address today. I'm going to do this with an R2R network, ladder network that we used in the Bit Crusher video that I did a while back. A link up here somewhere. And also an Arduino command called port manipulation, which is just low-level coding to directly address the pins of the ports. I'll explain this more in a bit. But basically, I'm just going to really fast put the value from the analog input to 10 ports on the 10 digital ports, and then which will go through the R2R network, and we'll get the 10-bit value out. This has been done many times before in many different ways. I want to try this today because I want to learn this for my future experiments and eventual modules that I'm going to build with this. So that's what we're going to do, and we're going to do it now. Let's go. First, I'd like to also say thank you to my Patreons who support me by joining me over on Patreon, and which helps me a lot by financing some of these projects for me on this channel. So thank you very much everyone who is doing that. And now let's get on with the project. So what is port manipulation? I found this site which explains it quite well. I like it because it has some tables to show you what a port is. So really, like if we go down to the hardware, a port is a collection of pins. So on the Arduino Uno and Nano and all those that use the 80 mega 328 chip, we have 3 ports. Port D, Port B, and Port C. And here on Port D we see that we have 8 pins, 0 to 7, and that is digital pin 0 to digital pin 7. So that's basically a 8-bit byte. On Port B we have, I believe, 6 of the pins, and that is the rest of the digital outputs of the Arduino, or digital pins of the Arduino. So, and then we have port C, which is the analog inputs of the Arduino. So port A0 to A5. So that are the 3 ports that exist in the Arduino. Those pins you can directly manipulate then with the DDR and port commands, which basically goes past all the Arduino IDE and just goes down to, I guess, assembler, and just writes directly to the hardware ports. So we need to do a few things. DDRB is basically we tell the pins of the port what they are supposed to do. So in this case we do DDRB, so that's the port we are accessing, and then we set, in this case we set Arduino pin 10 to an output. You can write it in binary, you can write it in hexadecimal. Then once you've done this, you can address the port or put values on the port pins. So in this case we do port B, again same port as that we set the pin 10 to an output. We set that pin to high, a 1, or we write like that and we set it to low. And if we set all the pins to outputs by writing 111 here, and then we can set all the pins of that port by just writing 1111 here, we can set all the pins on this port to high with just one command that is super fast. I'll put the link to this site in the description if you want to read more about how this works. Now, I've got an intern, Bob, or as some of you might call it, ChatGPT, and nowadays when it's just a simple code like this, I usually ask him to write it for me. So I asked him, I need an Arduino sketch that read an analog 10-bit value from a pot and then using low byte and high byte sends the byte to 2 ports. And he gave me this. Interns are not very smart always. They are still learning. That's why they are here. So he actually thought that by port I meant pins. So this one was a bit wrong, but it gave me an idea. So when we talk about dual PWM, but we'll get that in another video. So let's disregard that one. So I did a bit better command, instead use port manipulation to send the values to 10 pins. And now we got it a bit better. He does use port D and port B command for the low byte and high byte. That is nice that he uses this, but he only uses pin 2 to 11. I want to use the full port D, so I want to use pin 0 and 1 as well, which I've done in my sketch here. And I know people get a bit upset when you do that because they say that you might break your Arduino and because you can't program it afterwards. But you can. There's a small pause before the program that you've programmed your Arduino with starts, where it just checks if there's anything that wants to communicate with it on the serial port. So it's totally doable. I've done this on the Arduino I'm using for this project a couple of times now, changed the program and stuff like that. So but that means that we can't use serial, which he does. So I remove that, and then we read the analog value from the pot, and then we write the value with low byte and high byte. Very nice commands. And then serial print, we took that away, and the delay I also removed because that would make it step 10 times a second between the values. If I sweep with a pot, it would go instead of whew. So yeah, so actually he did complicate it a bit. This is as small as this program is that does this. Let's put this into an Arduino and build some circuits to show what this does. And this first circuit looks like this. So that simple code is then in here, and we've actually just put one LED into each of the ports 0 through 9 here, and just by a resistor, so a simple variant of, instead of putting a resistor on all of them, I just put one for all of them. And then a potentiometer connected to 0 volts and 5 volts. And as you can see, the downside of this is that now, instead of each value of this, like each fourth value of this being an output, now each different value I turn on this knob here will be a value, a new value up here. So just touching it and the value jumps around a bit. But we can see the thing that we are just in the lower 4 bits here jumping around basically. And when we turn this up, we light up more and more of the ones up here. Now we are up on bit 9, and there we are bit 10, and there we are at max, and they are all lit. And if we slow down a bit, we see that these down here start to glow, and we're slowly going up, 9 goes out, and then 10, and then we move down, and they slowly go down to those 5 bits down there. We can put in a smoothing circuit. There's a few ways to do that, but so yeah, here we have it. Let's instead of LEDs, let's build an R2R circuit instead. So what is an R2R filter? I did explain this a bit in the bit crusher video, but let's just go through the basics again. So an R divided by 2 are actually ladder DAC, digital to analog converter. So we need to learn these here, the LSB and MSB, that is the least significant bit and the most significant bit. And this means, so if we take the most significant bit, that would be the highest value of the byte. So in our case, the bit that by switching it we get a 512 value difference. So the bit that does the most change to the value, so the most significant bit. The LSB is of course bit 0, the one that just goes between 0 and 1 in the final value. So that's the least significant. You will barely see the change in this in the output value. And then you just add these in this ladder configuration, where you begin with a 2R, the value of the resistor, times, so if you only have one type of resistor, basically you put 2 resistors here to ground. Or if you have 2 values, let's say you have 1K resistors here, and then 2R would be 2K resistors. So 2R to ground, that puts the least significant byte very close to ground, so the value that it produces down here will be very small. It's a little bit difficult to explain, and I'm sure there is someone out there, if you really want to know, that can explain this better. But each intersection here is basically a voltage divider that divides this with the previous value here. So if we just take this value right here you have 5 volts. If you turn the least significant bit on, you have 5 volts going down through 2R, and then that is here 2R to ground, so that would mean that at this point you have 2.5 volts. And then that one is then voltage divided down here with the second bit that only divides, that has 5 volts here, and then divides to that 2.5 volts there, and then so the value gets lower and lower and lower the closer you get to the output, this value, I'm guessing, because that is closest to ground. And then these gets more and more, or not as much divided as the first ones down here. This in turn, so you can buffer the signal like this. In this, on my breadboard, I haven't buffered the signal, but you can do that. And then you need a kind of filter, like RC filter would be fine. There are loads of different filters to smooth out the signal to make it more analog, as to say. So an R2R resistor network is basically just a bunch of resistors in a ladder-ish configuration, going from the lowest bit to the highest bit, and basically what this does, we add another voltage, because it's a voltage divider in each step, basically from the previous step. So that way we get a smaller and smaller voltage for each pin, that when we put the pin high up here where there's at the first bits, it's a really low value, and when we do it down here on the last pin or highest value bit, we get a very high voltage, and that would then smooth out. Then we do an RC filter on this to even it out a bit, and that is when we get an analog signal out here. So let's plug this in instead. So to connect the R2R network like this, we need to have two terms correctly in order, MSB and LSB. MSB means most significant bit, and LSB least significant bit. And the most significant bit is the bit that does the highest impact on the signal. So that would be pin, or bit 10 in this case, the one that we light up the last, the one that makes the biggest difference, the most significant. And the least significant is the first bit that just barely does an impact on the signal. So that means most significant bit closest to the output, and that would be bit 10, so pin 9. And it's in the wrong, we need to do it like that. And then we just move down. So we can now listen to this signal and or watch it in a scope to see what's really coming out of this. So we moved over to the modular, and I have the circuit here and connected to the voltage volt per octave into this braids with a blow sound. And there's no filtering on this. This is raw digital or DAC output, so no filtering on this. And let's listen. And we sweep with the input knob into the Arduino. So this, I would say, is really good digitally. So this is digitally controlled oscillator right now. So so we have a smoothing capacitor, or a low pass filter, by adding this capacitor to ground from the output here. Really doesn't make that much of a difference. Because the signal was so smooth before, but I'm guessing if we watch in the oscilloscope, this maybe my oscilloscope doesn't have enough resolution for us to see the bits here. 1,000 steps on my little oscilloscope, I can't see that. So, but yeah. So I'm happy to see that my experiment actually worked. Now I can take a 10-bit signal in and put a 10-bit signal out. There was, of course, an error that my intern did that got me thinking and of another way of doing this, but using PWM. That's called dual PWM, which has also been done before in the Mosi library and lots of other places. So it has already been done, and there you can get up to 16 bits output if you want. So I'm going to, in the next video, I'm going to look at that as well, because that is a very good way of saving up on pins, because with this, now we take up 10 pins just to get an audio output, so we don't have many pins to do anything else with. So because of that, I think dual PWM might be a better choice. But we'll see that in the next episode. And until then, take care. Bye. Hello. Today I would like... Today. Hello. Hello. Today I'd like